por el retraso, sobre todo a quienes nos están esperando en los medios distantes electrónicos. Vamos a comenzar. Tenemos el honor de contar entre nosotros a la doctora Taisiya Mineeva, Taya. Ella es investigadora en el Centro Científico Tecnológico de Valparaíso, que depende de la Universidad Técnica Federico Santa María en Chile. Y ella realizó sus estudios doctorales en Estados Unidos trabajando en J-Lab, y es una física experimental que está interesada en cómo se forman los hadrones en colisiones, en particular inducidas por colisiones entre electrones y hadrones. Y recientemente coincidimos en una conferencia en dos cosas, no nada más en la conferencia, sino también en intereses científicos, porque la manera en la que se producen los hadrones en este tipo de colisiones o en otras, inducidas no solamente por electrones, puede ser muy interesante para revelar propiedades de estos hadrones, en particular su estructura. Y como nos va a contar Taya, parte de lo que ella ha estado explorando recientemente tiene que ver con si esta estructura se puede describir a estas energías como, por ejemplo, para un hadrón tipo lambda, como formado por un diquark y un quark. Y si eso sucede, podría entonces tener importantes consecuencias para otras observables relacionadas, por ejemplo, con el spin, que se pueden cuantificar en términos de la polarización de estas partículas después de la colisión en alguna interacción. Pero sin que yo diga más, dejo con ustedes al especialista. Taya, por favor, adelante. Creo que tienes que hablar más fuerte.
Well, Alejandro, thank you for this very nice introduction. Now I think I don't even need to give a talk, right? Yes, so thank you for coming this morning to the colloquium, and thank you for those who are joining on YouTube. We had some technical difficulties, so I'm going to use my computer to change to the slides, and I also don't have a pointer. So the title of my talk today is Emergence of Hadrons in Cold Nuclear Matter. I will start with hadrons and the strong force with a very general terms. I will try to make it general for the colloquium. Then I will talk about the cold nuclear matter, its advantages, and I will contrast the cold nuclear matter with hot nuclear matter, with which some of you are quite familiar with, I think. And finally, I will talk about the emergence of hadrons using phenomenological framework. And I will show you the wealth of data that we have collected so far in the experiments from Hermes and from Jefferson Lab. So I will start with the story that you know already. So ancient Greeks believed that atom was formed, well, atom was the smallest bit of matter. In the 20th century, the scientists split the atom and found out that it's composed of proton, neutron, and the electron. The proton and neutron themselves are composed out of quarks, and the quarks are bound together by the gluons inside the nucleon. So quarks carry the color charge. It comes in red, green, and blue, has nothing to do with aesthetics. And the gluon comes in the color, in anticolor, again, carries a charge. It is a color charge that is in charge of the strong force. So the color charge binds quarks inside the nucleon, and quarks inside the proton, and the proton inside the nuclear atom. And the strong force, actually, we cannot measure, as you know, the might of the strong force because it acts across subatomic distances. But we know that, for example, electromagnetic force is very well measured and much better understood. So what I will do, I will contrast and compare the work of the strong force with electromagnetic force. So the familiar process in quantum electrodynamics is the ionization of an atom. When we pull an electron from the nucleus, at the long distances, the potential energy decreases as the distance increases. So eventually, electron at a long distance will become free at the expense of some work done. And the analog of ionization of an atom QCD would be hadronization of the quark. When we pull quark from the nucleon, the potential is increasing with increasing distance. And for this reason, we don't observe quarks as quasi-free, because the force is actually constant, which I'm going to show on the next slide. So there are at least three differences between QED and QCD. One of the first differences is that the charge in the QED has two polarities, positive and negative, but the charge in the QCD comes in three colors, as we already know. And the second difference is that in QED, the photon is chargeless, and it doesn't have a self-interaction, whereas in QED, we have a self-interaction of the gluons. And for these reasons, the electric field and the color field are different. So electric field goes to infinity, and the QCD color field is actually comprised in a flux tube, yeah, between the quark and the antiquark. And finally, the other difference is the strength of the interaction. The strength of the interaction is measured in the coupling. So the coupling of QCD is around 1, and it's 100 times more than the coupling of the QED. But as we all know, that couplings are running, and they depend on the energy scale of the process. So yes, QED coupling runs, but the difference between measuring the coupling in QED at the zero energy, which is here presented 1/137, versus measuring it at a high energy like mass of the boson is roughly 10%. But when we talk about the coupling in QCD, the difference is much larger. So even in the range of where theoretical calculations are more or less comfortable, the coupling of the QCD runs by the order of magnitude. In this plot, you see the coupling alpha S plotted as a function of Q. So Q is the energy deposited in the system, and the other way to think of it is the distance scale, which we probe with Q. And the points here are experimental results from various processes. And these points are fitted with perturbative calculations. But first of all, I would like to say that to extract the alpha S, this is a fit done to the cross-section that is extracted, for example, in the collider results, or it could also be the fixed target experiments. And then they're fitted with next to leading order perturbative expansion. So when we go to high energy, and high energy means small coupling, and small coupling and high energy means it's possible to do, as you know, perturbative expansion. The alpha S is small, and the things will converge. So there is this domain would be associated with asymptotic freedom, where perturbation theory is applicable. However, when we go to lower Q and higher resolution, here we enter non-perturbative regime, where we talk about the quark confinement. This plot was taken from Particle Data Group 2021. And by this time, this is the amount of data that has been collected and the theoretical description that was available. But as you know, the field is very dynamical, and calculations of alpha S has been of large interest. And I would like to show you just a couple more plots related to alpha S. This is the calculations on the left by Alexander Dörr and Brodsky in 2016. I suggest you to refer to this paper. It's like a 200-page review of all the available models, renormalizations, approaches, etc. What is important to notice here is that alpha S freezes at a very low Q square, so it reaches some constant value. It is important to provide experimental data to actually being able to distinguish between the leading mechanisms and non-perturbative regime. So the plot on the right is talking again about the strong coupling, but in terms of effective charges. And the effective charge is used to more like a process-independent way to talk about the strong force and the couplings. And it can describe a large variety of reactions and experimental data. So here you see this is a plot, the most recent review from 2024. Again, it's a 150-page, very extensive review if you want to read about it. And it collects all the world data that is used to describe the effective charge. And the calculations, actually, from what I remember, they agreed to up to 1% with experimental data. Non-perturbative regime is described mostly by Dijkstra-Schwinger and holographic QCD. And then when you go to slightly higher Q, it's a description by generalized Bjork and Summerall. So this is about the strong coupling. I will go back to the simple picture of potential. And the reason I will be talking right now about the potential is actually to smoothly transition into hadronization process. The potential in QCD, the full potential is derived from QCD Lagrangian, and it's comprised of Coulomb part for third alpha S over R plus KR, which is confinement parts. So Coulomb part is important in short distances, and it's also important for the heavy quarks. When we go to higher distances, the linear part, the confinement part starts to kick in. The difference between quenched QCD and the full QCD is that in full QCD takes into account the potential, the interactions between quark-antiquark and quark-antiquark pair production, and it also takes into account the gluonic field. Yeah? So in quenched QCD does not take into account gluonic field, but quenched QCD is what is also used on the lattice because it's more calculable. Now the next slide will be about confinement on the lattice. So the question is, if we talk about the confinement and the confinement potential, which is KR, how does it work on the lattice? Well, lattice confirmed QCD calculations of the gluon field between static color and anti-color. And on the plot here on the right, this is the potential in lattice units as a function of distance. What is important here is this potential rises linearly, which supports the idea of confinement. Now, confinement. Probably many of you already know that the Clay Mathematical Institute that was established around year 2000 in Cambridge, Massachusetts, has emphasized 7 millennia problems in the mathematics. Those problems, they were decided by the scientific board, international board, on the classical mathematical problems. And one of these classical mathematical problems is to prove that SU3 gauge theory is mathematically well-defined. Mathematically well-defined in the way that it was formulated by Arthur Jaffe and Edward Witten is based on 3 pillars. The first pillar is to describe the mass gap for the vacuum, where the energy of the vacuum should be greater than 0. Then the second is a quark confinement, and the third is a chiral symmetry breaking. So this is a $1 million prize for those who can describe. This was postulated, I think, around 10 years ago, and it's still an open question. So confinement. If confinement is so difficult to describe and challenging to describe from the point of view of theory and exact calculations, what it means is that we have phenomenological models, right, as many of you work with. And what we do need as experimentalists, I'm an experimentalist, is to provide the data to support or improve some phenomenological models. To describe confinement, there are 2 categories of models, of experimental approaches that can be used and that have been used. The first class of models is to understand confinement through hadron spectroscopy and studies of exotic states. So hadron spectroscopy, it would be the resonances, excited states, tetra and pentaquarks. Exotic states would be the studies of glue balls. And the second approach, another approach in general, is to study the subject by introducing the string breaking mechanism. And this is what I will be talking in my talk today. So the string breaking mechanism, the idea is that a new QQ bar pair, as depicted here in the simplified representation, a new QQ bar pair would be created from the field of the initial Q and Q bar being pulled apart. When the energy is sufficient, the QQ bar pair will be formed and the hadrons will emerge and freeze out. So this is a general picture of the string breaking mechanism. The first string model was developed over 40 years ago right now, and it was a long string model, which uses linear potential to trace the string motion. So basically in the Lund model, it's like a popcorn model when you pull two quarks apart, and from the string breaking mechanism, mesons and baryons are formed. Important thing here is the string constant, the K, 1 GeV per Fermi. This is the energy that would be stored when you pull quarks apart. And the string tension was actually derived from the Regis slopes, and the Regis slopes come from the hadron spectroscopy. So the Regis slopes, it's when the square mass of the hadrons plotted as a function of orbital momentum is linear. And from this hadron spectroscopy, the string tension was derived. Lund string model works, and it gives powerful description of hadron production. And there is also a strong support of the Lund string model in lattice calculations. However, it doesn't have the ingredients of fundamental QCD. The string model, I think the string model was first presented by Nambu and Suskind to describe the Regis trajectories. And it was viewed as like a flux tube from a chromoelectric charge. And this idea was then put, and this is a representation of the expelled vacuum field when we pull two quarks apart, or when the quarks inside the baryon are pulled apart. This is a dynamical simulation, and you can see it from Derek Lineweber website. But I have to make a disclaimer that the flux tube model is not a universal model on which everybody agrees on. So flux tube model mostly works for the heavy quarks. However, for the light quarks, the story could be a little bit different. And the theory would be described through dynamical quark dressing. And for this, you can refer to the papers by Craig Roberts and Brodsky. But here, for the sake of general description of hadronization, I'm going to use more the idea of the flux tube. Now, how do we connect the world of QCD to the visible world? We do it through the process called hadronization, which describes the relationship between quarks and gluon and observable physical states. To study hadronization, we mostly employ two processes. The first one is the deep inelastic scattering of electron, where it exchanges a virtual photon with a quark. You saw this picture on the main poster of the talk, and I will show where this drawing comes from. But so for now, this is a deep inelastic scattering, and the nuclei here, we're not talking about nuclear physics. We use nuclei as an analyzing medium, as a tool. Deep inelastic scattering, and then we have heavy ion collisions. So this is a rare head-on collision when you have two partons colliding, creating jets of hadrons. And also, this is another way to describe hadronization. So the picture of deep inelastic scattering, this one, comes from the long-range plan for nuclear science. This is a plan that is developed by Department of Energy in US by National Station to define what are the priorities in the US, in the world, for the future of the nuclear science. And one of the hot topics that was highlighted is actually the studies of hadronization. What are the timescales of color neutralization and hadron formation? And what are the differences in hadronization of light quarks and the heavy quarks? So this is one of the questions highlighted in the long-range plan. And further on, if you look through the document, which is again a very long document, but it explains how it's possible to study hadronization in fixed target experiments and in heavy ion collisions. So let me first start with, here I will make a distinction between cold QCD matter and the hot QCD matter. Cold QCD matter basically is when we know exactly the environment in which we work on. So we have a nuclei of defined density, the size, and the properties that we know. And cold QCD matter would be deep inelastic scattering and the Drell-Yan. So in Drell-Yan, you have two partons which interact, produce virtual photon, and then they emerge as a dilepton pair. And the dilepton pair actually carries information about the quark passage. In deep inelastic scattering, we have information about the quark passage and the passage of the hadron, formation of the hadron. So in hot QCD matter, this is the heavy ion collisions, with which I will first to give a general slide. Depicted is central collision of two nuclei. In the initial state, they look like pancakes due to Lorentz contraction. Then once they become very close, there is a pre-equilibrium state that is formed, which is not a deconfinement matter yet, but very close to it. Once then they collide, there is so-called quark-gluon plasma formed. Well, this is a picture of the temperature in the head-on collision, right? Once the quark-gluon plasma starts to cool down, there is a process of hadronization, color neutralization, and finally, the hadronic gas is formed, the hadrons freeze out, and we experimentally measure the particles. So the conclusions of this stage, and this stage are made based on the observation of those hadrons. One of the ways to measure hadronization is to use the ratio of the ratio, let's say, of jets of particles in ion-ion collisions. That would be, for example, lead-lead in CERN, and normalize them to proton-proton collisions. So if this ratio is 1, it means that there is no effect due to nuclear medium. If the ratio is less than 1, we call it suppression. The ratio greater than 1, we call it enhancement. And I'm going to show just one plot to illustrate suppression. And this is an example of J-psi production, the charmonium production from Atlas. On the left here, we see the multiplicity ratio of J-psi as a function of participants. J-psi here produced through a fast decay. This is called the prompt J-psi. And non-prompt J-psi is produced through the quarks, energy loss, and reconstructed through the secondary vertex. What is important here is that we see that the nuclear medium does affect in the sense that when we have head-on collisions and more participants are involved, the more there is nuclear medium, the more there is suppression of J-psi production. So you have almost 80% of J-psi being absorbed. However, when you go to very peripheral collision, there is a very small suppression. And this suppression, actually, what is interesting, and which, I don't know, maybe you understand, I personally don't quite understand, is that it doesn't seem to depend whether J-psi was produced inside the medium, which is a fast decay, or outside of the medium, which is a non-prompt. We didn't actually measure J-psi in elastic scattering. It would be another era of measurement. That would be very interesting. And I think it will also help to shed light on the processes that happen in quark-gluon plasma. Yes?
Sorry. How can you distinguish between prompt and non-prompt?
That's a good question. So So the prompt production, I think J-psi is measured by from the muons. This is a muon pair. And non-prompt, I'm not an expert, but you have a secondary vertex because it's a different channel of decay of J-psi through the secondary vertex. And this is a difference between if it's muons, it's prompt. If it's a secondary vertex, and then I don't remember the mechanism, this will be non-prompt. Okay, so now I'm going to switch gears to Deep Inelastic Scattering from DESI, from Hermes, and Jefferson Lab. Elastic scattering. This is the most simple picture, and the most simple is the most analyzable picture that we can think about hadronization. X Bjorken greater than 0.1, we will have a direct virtual photon absorption by the quark. So once the quark absorbs the energy of the virtual photon, it will propagate, and it will emit gluons, will lose some energy. This gluon emission and energy loss happens in vacuum and happen in the nuclear medium, just rate is different. Once the color is neutralized and the propagating quark finds a partner, an anti-quark, it will form a color neutral stage, which we call prehadron. And then later, prehadron will emerge as a fully formed hadron. So here we distinguish the two stages, which were mentioned in the nuclear range plan report. But these stages, they've been defined much longer ago. They're not theoretical exact quantities, they're phenomenological tools that we use to distinguish between perturbative and non-perturbative regime. So first we talk about production length that is related to color lifetime. This is time of the quark following hard collision. And this is basically the time that is required for the system to neutralize its color. Once the color is neutralized, the gluon emission will cease, it will stop, and then we will be talking about formation length, which is a distance over which color neutral object forms a full hadronic wave function. So the two stages. And now, to study the effect of hadronization, we implanted in the nuclear medium. So what you see here is two nuclei of different size. So for example, this can be a carbon nuclei and this can be gold or lead nuclei. When the hadronization is, color propagation time is much larger than the size of the nuclear medium, color neutralization can happen outside of the nuclear medium. But when the nuclear medium is so large that the color neutralization is happening inside, the hadrons most likely will be attenuated in this nuclear medium. So what we do, we basically use nuclei of different size that act as a ruler. And the effect of the size of the nuclear medium will be manifested in the modification of the observables that I'm going to introduce right now. Well, first of all, the two important hadronic variables, Z is a fraction of the energy that hadron carries, the fraction of the initial energy that you put in the system. And the other is hadron transverse momentum, and it's transfers to the initial virtual photon direction. This is the main hadronic variables. I think the other ones you're probably aware of, Q square for momentum transfer, and nu is the energy transferred. Now the observables, which are changing depending on the nuclear medium. The first observable is transverse momentum broadening. This is an enhancement of transverse momentum squared on the nuclei compared to the same quantity in deuterium. And transverse momentum broadening connects to partonic phase, to the quark propagation phase. I'm going to show you, this is a real distribution of transverse momentum broadening. So you see transverse momentum on nuclei, the shape is different than compared to the deuterium. And the second observable that we use is hadronic multiplicity ratio. It is number of hadrons in nuclei compared to the number of hadrons in deuterium, everything normalized to the deep inelastic scattering, to the number of electrons. And hadronic phase is sensitive to hadron formation and attenuation. Now, to draw the connection between heavy ion and fixed target experiment, multiplicity ratio in fixed targets is practically similar or the same as the ratio in heavy ion collisions. So what we have in multiplicity ratio in deep inelastic scattering is probability of the process in EA normalized to ED, nuclei to deuterium. And again, we talk about separation and enhancement when there are nuclear effects. So I'm going to show you an extraction of the color lifetime. And this extraction is based on the Hermes results on transverse momentum broadening and multiplicity ratio. Well, Hermes was the first collaboration to identify hadrons and the first to really publish data on hadronization. And the initial idea was not only to measure the time scales, but also to understand what are the mechanisms of hadronization. Is it all about quark energy loss? Or is it about hadron absorption? Or if there is a quantum mechanical interference between these two processes? About those, I'm not going to be talking about in this talk, the phenomenology of various models that we have. But I'm just going to show you an interesting extraction of color lifetime that was done in our group later, a decade later after the data was published. So what they did a simultaneous feed of these two observables. The feed is here. And they use a very simple geometrical model. There is no dynamical information. Basically, you have information about the density, the hadronic cross sections, and quark phase is related to transverse momentum broadening and hadronic phase to multiplicity ratio. So the important message here is the color lifetime was extracted. It depends on Z, on the energy of the hadron, and the values for the color lifetime is somewhere between 2 femtometers and 8 femtometers. And what does it tell us? That in Hermes kinematics, which is 27 GeV electron beam on fixed target, in the Hermes kinematics, the lifetime of the quark is comparable with the size of the nuclear medium. And this is very interesting. Now, what supports this geometrical model makes sense is that they also were able to independently extract the Lund string tension, which in their model came to be 1 GeV per Fermi. So in a way, this validates the results. And now I'm going to show you some data. I think I'm just going to flash the data, but to show you the wealth of information that we have accumulated for hadronization studies from Jefferson Lab. Well, Jefferson Lab was conceived, I think, in 1983, initially to do the hadron spectroscopy. You remember the first class of models that I told you about? Jefferson Lab started with hadron spectroscopy. Right now, the flagships of Jefferson Lab program have expanded to include DVCS, GPDs, TMDs, and actually short-range correlations, and of course, hadronization. So Jefferson Lab is located in Newport News in Virginia. It's been in operation since 1995. It started with 6 GeV energy, and then it was upgraded to 12 GeV energy. With 6 GeV energy, basically what you have is injector of electrons. Electrons are accelerated in the LINAC part of the accelerator. Then they're bent to the second accelerator module. And this recirculation happens 4 times at the 6 GeV. When we have an upgrade done, what they did, they added several more cryo modules to accelerate electrons, and they added another recirculating arcs to make more passes, and the energy reached to 12 GeV. And also importantly, there is an additional experimental hole to study glue balls and exotics. So Jefferson Lab is comprised of almost 2,000 users. This is an older picture, 278 institutions from 39 countries worldwide. So it's a very big collaboration of scientists. And I'm going to show you some results from the previous era, from 6GeV, when we had class spectrometer. It's almost a full pi detector, which is capable of very good identification of charged mesons. Also, we can identify baryons. And the experiment that was done, we had two targets in the bin together. So that was nuclei and deuterium. And we have results on light and heavy hadrons. This I'm not going to go into details, but what I want to emphasize that as we continue the studies of hadronization from the Hermes era, Hermes were the first one to identify charged hadrons and neutrals as well. In Jefferson Lab, we expanded the dimension of the measurement. So we can measure hadronization in a multidimensional way. And why do we need to measure it in a multidimensional way? Again, is to distinguish the leading mechanisms, because after Hermes data was published, there was much more light shed on the hadronization. However, there is a lot of questions left. So what we need to access to more mesons, to more hadrons, and we also need high statistical data. And we can do it in Jefferson Lab. So we have three-dimensional data for charged pions. We have three-dimensional data for neutral pions, and this is world's first measurements. And we also have access to rare hadrons. This is very small statistics, but we have access to it. We can measure transverse momentum broadening. And now I'm going to switch gears to baryons. And baryons is an interesting thing in terms of, and I will finish with this in terms of access to heavy ion collisions. So lambda identification, I'm going to talk about lambda. Lambda was identified through its invariant mass from pi minus proton decay. And here on the left, you just see invariant mass of lambda for iron and for deuterium. You see for heavy targets, we have much more background, which makes it more challenging to work with nuclei. And on the plot on the right, you see transverse momentum and transverse momentum squared. This is the first measurement of multiplicity ratios for lambda. And if you notice, they are plotted separately. First plot is z from 0 to 0.5, and the other one from 0.5 to 1. Why is it? It's because we distinguish here the so-called target fragmentation and the current fragmentation, two different regions. And also because we would like to emphasize that in z less than 0.5, there is a lot of things happening at low z that we don't really understand. And we don't really understand in terms of the description with phenomenological models. There is a huge enhancement here. It's 6 times more than what we see for pions. Pions we can describe currently. Even multidimensional data well described, but lambda is much more challenging. Now, when we go to high z, z greater than 0.5, the suppression actually for lambdas is less than for the pions. So again, the behavior is different for baryons. Transverse momentum broadening is also different. And the multidimensional data, what I mean by multidimensional is transverse momentum broadening is a function of z, is again not described by the models that are capable to describe mesons. So what's going on with lambda? Its transverse momentum is actually magnitude larger, multiplicity ratio enhanced, and very similar behavior with protons. So lambda and protons have similar kind of pattern and ordering when we look at the multidimensional data. Could it be possible that a virtual photon is absorbed by the dye quark? This is one of the questions that can be addressed with deep inelastic scattering. And why? Why can we study with deep inelastic scattering? Because, you know, for proton and for lambda, you have common U and D, quark or diquark. Then you have a different spectator. So it would be very interesting to measure with more data and more statistics and compare proton, neutron, and lambda. Will they behave similarly because they contain a diquark, or will there be differences between because the spectator is different? Of course, you need to have more theoretical work to determine the feasibility of the studies. So if some of you is interested, in the future we will have much more data that I'm going to show you that will allow us to distinguish and to really pinpoint the mechanisms. Because as you know, diquarks, they have been in the QCD ever since QCD was conceived, right? But one of the challenging things is to describe it experimentally. So we can think of all the avenues where you can reach for diquarks. This is the experiment that I just mentioned that we have just run half a year ago, and we collected much more statistics. It's the same idea using the double target, but this time it's with higher electron energy and with new class spectrometer. We will have, well, with the data that we have collected right now, we just collected the half of the data, because what PAC, the committee that assigns number of days, what they do right now is they give half of the time to run an experiment, and the other half, I think it should come in like a couple of years later. But already with what we have collected, we have a huge data that will allow us to study rare mesons, heavy quarks, baryons, and of course, neutron, proton, and lambda. Now, to finish, I will have a few more slides on the lambda, and this is what Alejandro started his introduction with. The lambda, the interesting lambda. Here on the slide, I put the results from the measurement of lambda polarization in the gold-gold collision. So as you know, when you collide two gold nuclei at a very high energy, the state of matter that is formed looks more something like a fluid. If your collisions are peripheral, then this fluid is likely to exhibit vorticity. And vorticity implies that you will produce an intense magnetic field. And the intense magnetic field implies that there will be spin-orbit interactions, couplings, with the magnetic moment of the particles, right? So lambda, the reason lambda is interesting because it has a self-analyzing power. And the matter as a fluid that is formed and the vorticity and the magnetic field would likely to affect the polarization of the particles. So measuring lambda polarization, I guess it kind of gives impact to the models to describe the hydrodynamic of this fluid. I know that you're an expert here, but please correct me if my understanding needs some more complexity. But as an experimentalist, I would like to say that the lambda polarization is interesting because the proton tends to be emitted in the direction of the parent lambda. So you can take the proton and the lambda and measure the angular distribution between the two of them. And here, this depicts one event from star collaboration from the detector of lambda decaying into proton and pi minus. So star collaboration, they measure this polarization for lambda and lambda bar. And this is the results extracted. So polarization changes from 2 down to almost no polarization. And an interesting thing is that lambda and lambda bar polarization, they seem, both of them, they're positive, but at the low energies, there is a huge gap between the two. So would it help to check the consistency between hydrodynamical models if you know a little bit more on lambda polarization from cold QCD matter? And I looked through the measurements that were available in the fixed target experiments for the lambda. And the only one that I found is the one that was measured by Hermes collaboration a decade ago. Hermes had, well, so the difference here, this is a fixed target experiment, and Hermes had a linear polarization of the electron beam. In a fixed target experiment, the angle that you measure is between the proton and the normal to the plane that contains the electron beam. But the idea is the same, is to measure the theta angle. Here, the lambda is again the same analyzing power of the weak decay, the same as heavy ion, the same as fixed target experiments. And the polarization that was extracted by Hermes is actually a transverse polarization. That was extracted for a variety of nuclei, from hydrogen to xenon. You see that for a very high atomic nuclei, the polarization goes to 0, whereas for the light nuclei, the polarization could reach up to 7%, 10%. So there is a huge disperse relationship between the polarization and the nuclear medium. Where I'm going with this, I'm going to the lambdas that we can measure in class 12. What I'm showing here is a very, very preliminary results. You know, since we had an experiment done just half a year ago, the data actually is not finished to be, calibrations still are in process, and detector alignments and a few details here and there. So once everything is put together, actually the data will look even better than what I'm showing now. My point here is that we can measure lambda. This is a lambda peak from pi minus proton, and we have a huge statistics. So these statistics I'm showing for 5 targets. We have carbon, aluminum, copper, tin, and lead. And you see this is not even a fraction of all the statistical data. And this is already kind of multiplicities that we're able to extract. These multiplicities, there's no surprises, look very similar to charged pion multiplicities, but a lot of statistics. So can we access the measurement of the polarization observable from lambda by extracting the angle between the proton and the lambda 4 vector? So if somebody of you might be interested to work in this theoretically or experimentally, you're very welcome. There is an agreement between UNAM and my university where I come from for exchange of students and researchers. So I think this could be one of the fruitful fields if any of you is interested to work on. And this was my last slide. This is my last slide. So where I'm going with this is that 12 GeV is a current state of art, current state of experiment. But Jefferson Lab will undergo most likely an upgrade to even higher energy, 22 GeV. And this upgrade is foreseen to happen before the construction or the complete construction of the electron-ion collider. The difference and the beauty of this upgrade is that thanks to the new magnet technologies, we do not need to add more cryo models to JLab. When we did upgrade from 6 to 12 GeV, we added cryo models and recirculating arcs. Now with the technologies that was developed in Cornell University, we can replace the high energy arcs with fixed field alternating gradient magnets. This is a new technology. It's less expensive than adding new cryo models and building more arcs. So from the financial standpoint, this project is quite feasible. So again, the lambda will come handy at 22 GeV. There's a long life for the lambda. And with this, I am going to summarize. So as I showed to you that we can extract microscopic information on the color lifetime and hadron formation times using hadronization and deep inelastic scattering, where we know the medium, we know the kinematics. The observables that we use to extract information hadronization is transverse momentum broadening and hadronic multiplicity ratio. I showed you a vast pool of pion data that is well described by Monte Carlo models. In this case, it was Gibu. However, the lambda and the baryon data, they do need much more understanding. Perhaps the hypothesis as a diquark comes handy in explaining these differences. At 6 GeV, we had high luminosity data. In class 12 with 10.5 GeV, we already access a huge amount. We already collected a huge amount of data. We can access 4-dimensional multiplicities. And there is a grand potential to measure lambda polarization. With this, I'm going to finish and just mention one more thing, that we will have a conference in Chile from 6 to 10 January. I have checked that registration is still open in case some of you might be interested to come. And if not a conference, there is also a school following the conference, the school on machine learning in physics that will be held also in the Universidad Técnica Federico Santa Maria in the second week of January. All of you are very welcome. Thank you.
Thank you very much, Taya. I want to start the possible questions, if there are any. Asking you a question, because see, it seems to me that the picture of a proton, or for that matter, a hadron, depends on the energy. So in other words, when you bombard it with, say, long wavelengths photons, then what you can probe is the overall structure, not detailed structure of the proton or hadron. Whereas when you increase the resolution with a larger energy photon exchanged, then you start probing details. And of course, if you increase a lot the energy, then you're going to break up the system. This is deep inelastic scattering. Now, at the energies of class, my guess is that, well, JLab, my guess is that the energy is not that large enough. In other words, you're still breaking up the hadron, but still what you're saying is that you can analyze the propagation or the formation of another hadron within the medium that is the hadron medium, called nuclear matter, if you wish. So the first question I wanted to ask you is, how do you reconcile the picture in which, in my mind, naive mind, you break up the nucleus, but still you're saying that the formation could happen, the hadron, the final hadron formation, the one that you're targeting to measure, could form inside this broken up nuclear matter. Am I making sense in the question?
Yeah, I actually have a correct understanding of the whole process, and this is a correct picture. Yes, I agree with you, and it's a very good question. So the question is,
you broke up the nucleus, and still you're saying that you can form the hadron that you want to detect, pion, say, or the lambda, inside cold nuclear matter, regardless of the fact that the nucleus was broken up.
Well, then how do we define the broken nuclei? Because, so if you think about the lower energies, this is what you started with. When you have a lower energies, you can have elastic scattering, quasi-elastic scattering. You can form excited state of the nucleon, like resonances, right? This is one regime. Then the other regime is when you have a deep inelastic scattering, when you go even deeper and you probe the quark structure. And of course, then when you go even higher energy, you'll probe the gluon structure, right? Like EIC. So this is different energy regimes. And how we distinguish between them kinematically, experimentally, I guess is your question. And then how can we say that, yes, in this regime, my nuclei is not broken, but I'm forming a hadron inside the nuclear medium, right? Okay, so actually, this is one of the things that I didn't mention in my talk because I didn't want to overwhelm, but we have a kinematical selections of this region, right? So in order to exclude the regime when we can possibly produce an excitation of the nuclei or break up the nuclei, we put the cuts on the Q square, the momentum transferred, then we put cuts on the missing energy or missing mass. And this would be, for example, some of the theorists will argue with us, especially in Hermes. In GLAP, we say that deep inelastic scattering and probing the quark structure will be Q squared greater than 2, W squared greater than 4, the missing mass. In Hermes, they started at slightly higher values of Q squared. I think it was around 4 or 5. So when we put these kinematical constraints on selecting the sample, we ensure that we probe this deep inelastic scattering. Yeah. So then within the deep inelastic scattering, when you hit a parton, from my understanding, you don't really break up the nuclei. You pull or you kick the quark out of the nuclei. And through this hadronization process, whatever happens there, depending on the energy, as you said, this whole process can be carried out outside of the nuclei where it was hit, or everything can happen inside. So then you have measurable consequences, whether it's happened inside or the outside. So we know that when we have a lot of suppression, for example, most likely that at this kinematical phase space, the whole process happened inside the nuclear medium, right? Because there is more absorption, there is more hadron absorption, quark energy loss, etc. But when you kick out the parton and you see that almost no nuclear effects, well, it means that probably something happened out. Of course, Alejandro, I'm talking about inside and outside, there is interference, but roughly speaking, this is an idea.
Right. I'm sorry to monopolize the questions. I have another question. I think I have a better picture of what you just described, and this brings me to the second part, which has to do with the dispersion of this virtual photon with either a quark or a diquark, which is more or less the picture that you have in mind, and perhaps also it's actually a very interesting picture. It could mean or be a means to explain your data.
That's nice to hear it from
theorists. No, I like it. I'm not an expert, but I like it. But the question I have is, imagine that I can perfectly think of a proton or a neutron, more a proton than a neutron, being formed of a diquark and a quark. And therefore, if you come with your electron beam and exchange with this given proton through a virtual photon, the virtual photon, and then it can scatter from either the U quark or the diquark, UD diquark. Now, what happens if you form a lambda? If you form a lambda, then probably you stroke a U or a diquark, and if you do, then you break the proton up. So you get a U and a diquark, and then this diquark somehow picks up some S quark from vacuum, C. And then there should be a correlation between kaons and lambdas formed, because one of the S bar will go to the stroke, most likely U quark, or and then if you measure an abundance, an overabundance of lambdas, you may also observe an overabundance of kaons, and there should be a correlation between these two measurements. And second, once you do that, if you strike a U quark or the di quark, the polarization properties may be affected because, see, the di quark most likely is in an L equals 0 state, whereas the quark carries the whole spin, right? So there should be some way of, in this picture, to relate your abundances with also polarization properties. This, I understand that I'm not saying anything coherent. I'm just
No, that makes
expressing
a good
ideas.
exploration.
Yeah,
a good
for
pool of
exploration.
ideas.
Yes, exactly. So I don't know if you have any wisdom words on this, but it's just because I am very interested on these kind of things. And
Andres, this is really interesting. Well, actually, we were talking about also the kaons. We have a measurement of K short from 6 GeV. I didn't show this because we had a very small amount of data and statistics. But in the class 12, we are going to measure the kaons. And this is a very good point to compare.
Maybe the correlation is with K stars, like with
stars.
You know, spin also can be playing a role. So instead of just a kaon, a meson, with spin 0, it could be with spin 1. This is just, very...
That's interesting. Well, we need to see if we can access it.
One needs to sit down and see what... Okay.
It's very interesting.
But
I will bring it to our collaboration, to compare the kaons and the lambdas, see how multiplicity ratio behave. That will indicate us the effects from the S quark, picked up from the C quarks. And then contrast lambda with protons and neutrons, but also contrasted with a potential spin that can be in kaons in S quark.
Great.
That's very great.
Okay.
That's a great idea.
Thank you.
Thank you.
No, but yes, I actually like this kind of discussion. So sorry to have monopolized this discussion. Any question? Let me just emphasize something. Taya is, well, you've seen, she's very coherent and enthusiastic, and she's looking for students that may be interested to collaborate, not only from the theoretical point of view, most of you are theoreticians, but also from experimental point of view. If there are some interested people, and you may always talk to your friends and tell them to either work in the experimental aspects or the theoretical aspects, please approach Taya. She's going to be here today, and you can always write to her by email. She's very approachable, and she's very enthusiastic, as I said. So with this said, please, are there any questions?
Why this specific number in energy in this last upgrade? You mentioned this 22 GeV. Why this number? Is it the maximum you can reach with this technology, or what's the reason?
Technology. Yeah, the technology. So from what I understand, as I mentioned, when we went from 6 to 12 GeV, we had to add cryo models and an additional arc. For the 22 GeV, the cryo models stay the same, but you double the circulation of the electrons. And for that, you need new fields, new technologies to bend the electrons to go around. So from 12 to 22, yes, this is based on technology. You would think 24, but again, right now, for example, the last experiment we ran, it was not 12 GeV, it was 10.5 GeV, maximum is 11. So you double the 11, it's 22. Yeah.
More questions? Maybe in online? No?
No questions.
Questions?
I see one more question.
Oh, sorry.
In the collisions between gold and gold, what energy are the beam of the goal. I don't know if you say what energy is, and in that collisions.
You mean for the star collaboration?
Yes.
That's a good question. Let's see what I have on my slide. I don't quite remember, but there is a center of mass energy, right?
Yes.
So the center of mass energy goes above 100 GeV.
200
Yes, 200.
GeV.
Yeah. 200 GeV per nuclei. Per nucleon. No, per nuclei. Per nucleons in the center. Yes.
Yeah, it's a great number. I work 10 MeV. I'm nuclear physics. 10
Yes.
MeV is a lot for me.
It's like the
It's like
this is
High energy. But then Jefferson Lab energy sounds like a high energy for you too, right?
yes.
But do you think you can extrapolate your calculations from lower energies to just a few GeV center of mass? Because in JLab, our center of mass at 10.5, it's around 5 GeV center of mass.
Yes. Well, thank you for the question.
Thank you.
Sino is a low energy experimentalist, and so he's not working with models as far as I understand, but I may be wrong.
Well, that's great. In your group, you cover all the energy from MeV to very high.
Right.
GeV,
Well,
right?
these guys know a lot of things anyway. More questions? Okay. If not, please let's give Taya a great thank.
Thank you.
And don't forget to approach her in case you have questions or you want to collaborate. Thanks again, Taya.
Thank you. Bye. Online. Bye-bye. Thank you.